CMOS platforms for silicon quantum technology.
Yeah, thank you very much, Jimmy. And yes, I'm really happy to eventually manage to come here. And I realized that JQI and actually, at least part of the people in JQI had quite some influence on my research in the latest years. So Jimmy actually mentioned my work on superconductor hybrid systems, which has been a kind of my favorite baby for some time. And I had almost dropped in until some people from here came out with some crazy proposals to find the zero bias anomalies. And I had to come back and look at it again. So, but I must say, most of my activities right now are in this area, and that's a little bit not an accident. It is also coming from the fact that when I went to Grenoble about 9 years ago, I realized that Grenoble is actually one of the 2 places in Europe where people like a lot silicon. And there are essentially 2 main microelectronics centers in Europe. One is IMEC in Belgium, and the other one is late in Grenoble with the large-scale CMOS facilities. And so I thought this was a great opportunity, and since I was interested in quantum spintronics, okay, so that more or less made it happen. So today, basically, I'm going to tell you a little bit about the progress we've made over the past years, and I'm sure I would have as much things to tell you about what we've done and as the things that we want to do, actually. It's really work in progress. So I hope you will appreciate this. So when talking about quantum computing, of course, the key issue you will all agree upon is is scalability. So make system integrate qubit to large scale. And for scalability, for sure, one possibility to use solid-state system, the advantage is that, in principle, we can implement it on large scale. And so this has been done, for example, in the recent years with, for example, with the superconducting qubits. That's pretty much the state of the art in terms of solid-state quantum computing. And these are recent results showing first implementations of quantum error corrections with superconducting circuits. But as far as semiconductor approach is concerned, and in particular silicon, there is certainly some delay. And in fact, if you look at this, some sort of Moore's law for superconductors, we see that so the superconductor came out. The first qubits were realized just before 2000, Nakamura's work in NEC, and then so there has been a kind of steady improvement in their performances, measured by, for example, by this quality factor, the number of operations that you can do over the coherence time. And that's definitely this improvement that has allowed nowadays to the possibility to realize more complex circuits for implementation of quantum error corrections. And but you see, silicon had actually they started also around this time. There were these 2 seminal proposals from Lawson Di Vincenzo and from Bruce Kay, who must be somewhere perhaps here. And it's an interesting story because, in fact, I mean, I know for sure what happened in the 3.5 community. Around this time, we were interested in something very different. Cone effect was one of the things. So Daniel Loss had a hard time to convince them starting in doing qubits. And this took some time, actually. The first experiment started around here. The first qubit in gallium arsenide appeared around here. For silicon, I think they started pretty early, but it took a long time, actually, and I think most of the work most of the effort was happening in Australia, and it took a long time before the first qubit appeared, and that's, I think, mostly due to the fact that from technological point of view, it was difficult to engineer, develop efficient qubits. But then you see here, this kind of, I picked up some of the most significant results in the latest year. So you see there has been a quite important improvement. And nowadays, the best silicon qubits can perform at least as or even better than superconducting qubits, at least at the single qubit level. So there's quite some excitement and interest in this area. Of course, one of the motivations for looking at silicon is that when looking at thinking about scalability, well, that's the material where the technology is the most established one in terms of integration. It's CMOS technology, so that's an additional important reason for looking at silicon qubits. So at the moment, a number of single qubit implementation, single or two qubit implementation have been realized in silicon with kind of different approaches. All of these have been developed in academic labs. So you can see here work from Australian. This one is in HRL, and this is from Madison and Delft, and also similar work in Tokyo. And perhaps I missed some other group. But, so anyway, we are at this level. And now, in order to realize more complex systems, we need to perform large-scale integration. And so then you have essentially, that's where, in principle, CMOS technology can be helpful. And so what a possibility is to take these designs, these processes, and try to implement it on an industrial scale platform. And for sure, I know that Andrew Jurak has been going around recently looking for a partnership with CMOS foundries for doing that. Yet, one has to realize that this world and this world, the academic world and the microelectronics world, are pretty distant from each other. And there is communication issues. There are different let's say, rules somehow applies. And I've experienced this myself. In the beginning, actually, this communication wasn't working that well. And you know, in the CMOS, they have been contracts with industries. They have to comply to certain rules, processing rules, and so on. So there is not much flexibility. So you may have heard that recently our friends in QTech Delft signed a partnership contract with Intel. So I'm sure that they're probably going to look at this issue, transferability. I don't know exactly how. So in Grenoble, I'm going to tell you what we have. In Grenoble, we have at least the advantage that the microelectronics laboratory and our laboratory, they sit in the same place. So this is the CA campus, and to which I also would like to mention proximity to the CNRS colleagues that, let's say, are also in more fundamental science and quantum science. So that's certainly an advantage. And this was, for me, a motivation to start working in this direction. And so in Grenoble, in particular, we have this laboratory that counts around 2,000 people that has a 8,000 square meter clean room that can handle both 200 millimeter and 300 millimeter wafers. And so, and there has been a collaboration between my institute and this institute for about 15, 20 years almost. So we know each other pretty well. But something has happened in the latest year, in a sense that in the latest year, we managed to get some some funding, mainly for Europe, for the European Union, and then we changed gear. In the beginning, what research was going on, like, hey, I have some sample in my drawer, can you do something with it? And yeah, you don't go very fast like that. But over the last years, we're managing to make, in these facilities, devices the way we would like to have. So that is important news. So here is our approach. Instead of starting from a prototype developed in a kind of academic lab with flexible tools, we want to start right away from this platform and implement in this platform proof of concept devices that have qubit functionality. So in a way, we want to sort of start by quantumizing transistors. And as I will show you today, actually, there's not a transistor that you may even carry in your pocket now is not that different from a qubit. It can perform as a qubit at low temperature. Right, so some words about the technology we use. It's not the same technology that is used in Intel processors. It's based on FinFET technology. It's an alternative technology that relies on silicon-on-insulator wafers. So there's a layer of silicon on top of a so-called box, silicon oxide box. And then to realize transistor, the upper layer is etched away. So first by deep UV patterning, and then there's a trimming process that allows to thin down the channel region of your transistor. So you can thin this down to a few nanometers if you want. And then later on, to make a transistor, you need to add another step to define your gates. That's another UV lithography step. And here you have your three-terminal simple device. So this device is in this called a nanowire transistor, field effect transistor. And so if you look a little bit closer, this is a longitudinal cross-sectional view of the transistor. So you see the channel here. This is the silicon channel, undoped usually. And then you have some epitaxially grown source and drain regions. And here you see the gate. It's a stack of different material. First, you have an oxide, usually containing IK oxides. And then you have TN, is a metal, and then some polysilicide. Right, so you see also another cross-sectional view now in the transverse plane. And you see that this transistor, for example, is a kind of a rectangular shape. Which allows you basically to deposit your gate on 3 of its facets. So that's very important to maximize the gate coupling to the channel. It's a little bit the same principle as in FinFET technology. So you have a gate that surrounds the channel and gets the highest efficiency for gating. So we are going to work on this kind of material. So as I said, the collaboration between us and Leti started long ago, and in the beginning, we observed things like Coulomb blockade effects. Actually, I wasn't even in Grenoble at that time. So this was some kind of old measurements showing the characteristic of a transistor at very low temperature. And in fact, a field effect transistor turns into a single electron transistor, which has a kind of metallic character. For the experts, so these white regions probably recognize these are Coulomb blockade regions where the transistor channel is holding a constant number of electrons in each of these diamond-shaped regions. And you see the regularity of this pattern tells you that basically there is not internal structure. So it's like a metallic island of which we add consecutively more and more electrons, okay? However, you see here another example is a similar pattern with kind of diamond-shaped region defining Coulomb blockade regime. but here you see that the sizes of this diamond region is quite inhomogeneous. And that is a signature of the fact that you have an internal energy structure. So your transistor is more looking like an artificial atom. And the difference between the size of these diamonds reflects the energy scale quantization in the transistors, which is here is negligible. And this in particular, it's a measurement taken on a device where transport occurs by resonant tunneling via an individual dopant atom that is located in the channel region. So that's a little bit the kind of energy band diagram you should think of. So inside the channel, you have a few dopants, and you can occasionally put yourself in a regime where electrons go through an individual dopant. So you can call it a single atom transistor, if you wish. And so we also managed to do a similar experiment, but this time, instead of using one single gate, we use a split gate geometry, like this one here, and that allows larger tunability. So you have two knobs now to tune your energy levels in the channel. And that is something that you can use, for example, if you have a couple of dopants in the channel, you can independently tune their level such that you are able to come to a resonance relation. So you can align the two levels with these two knobs and then measure transport across a series of two donors. So this is a two-donor transistor. And an interesting experiment that we performed was to look at what happens when you connect an RF signal to one of the gates. So you basically oscillate at RF frequency one of the two levels. And this results in photon-assisted transport across this double donor. And the photon-assisted transport, you can see it here. That's a color scale measurement of the current, of the DC current through the double dot device. And you see there is a bunch of lines that denote transport via multiple photon-assisted tunneling. So you have one photon, two photon, three photon absorbed, or one photon, two photon, three photon emitted, up to 7 in this case. And so it's interesting to see that this pattern has also some modulation in the amplitude direction of the field. So this is the amplitude of the RF field. And the current is modulated, and this is an interference effect. It's a quantum interference effect. It's called Landau-Stuckelberg-Zener resonance, Majorana even. And it's a quantum interference effect, analogous to a Mach-Zehnder interferometer, if you want. And it reflects the coherent nature of the motion of electron between the two atoms. And we can extract from that, for example, the coherence time for the orbital motion of an electron between two donors. And this happens to be in the range of a few hundred picoseconds. So it's kind of short time, but that's not a surprise. A charge is typically decoheres with relatively short times in the range of nanosecond or sub-nanosecond. But if, in a way, if you want, is some kind of charge qubit device. More recently, as our focus moved more and more towards the realization of spin qubits, then we started to address more in detail the issue of understanding and evaluating the level of control of charge confinement in this type of devices. And so, for example, we realized that in a transistor like that, because of some, let's say, electric field focusing effect at the edges of this structure, over here, you have the minimum of the potential when you apply an attractive gate voltage, for instance, a positive gate voltage in the case of N-type transistors. So the highest confinement occurs here in the corners. Yes? So even if you have a structure that is relatively large, you end up having the formation of quantum dots that are tiny and located in the corners. And these quantum dots can have pretty sizable quantization energy, at least in the millivolt scale, and also relatively large charging energy. 10, but recently we even reached almost 100 millielectron volt scale. So this is a simulation that shows you that exactly this is not a surprise, this is exactly what should happen. And you have a plot of the density of carriers in the channel with the condition, an arbitrary condition that you should have in the channel an average density of 1 electron. So if you impose this condition, even if the charge is a kind of continuous variable here, it's not discrete, there's no Coulomb effect at all, but anyway, you realize that in a clean transistor like that, you end up having two 1D channels formed at the corners. And so that's in the case in which the gate and the channel length coincide with each other. We call this the short spacer case. However, if your gate is kind of narrower than the length of the channel, it means that you have two regions here that are not gated. Then, by applying a positive gate, you end up forming a kind of minimal of potential also in the longitudinal direction that will result in the formation of two dots. And you can have two dots also if you take into account, for example, the role of possible oxide charges, possible charges in the dielectric stack, which is possible. And then this also can result in some confinement that is a little bit less deterministic. And we probably also have been observing this kind of confinement regimes. So, but anyway, what you should bear in mind is that in a transistor like that, regardless of really the size, you can form pretty tiny dots on the two corners that can host a few electrons. Now, another important issue, if you want to realize qubit, once you have been able to localize a pocket of electron, maybe one or two or a few, then the other issue is to be able to manipulate the spin degree of freedom of this electron. So there have been different schemes that have been developed in different systems, and here is for the case of silicon. One possibility is, let's say, the most standard one is magnetic driving of the spin. So this is done by, for example, microfabricating a metal line close to your qubit. And this, by passing an alternating current, will generate an alternating magnetic field perpendicular to the static field that, as in NMR, will induce a coherent rotation of the spin. The disadvantage of this is that frequencies are typically relatively small because of the fact that you can apply relatively weak magnetic fields in this way. The other ideas have been introduced to speed up the manipulation, and one possibility is to add ferromagnetic elements that create a stray field, non-homogeneous stray field, so a gradient in the field. So now, by shaking electrically a quantum dot in this gradient of magnetic field, we can effectively have an alternating magnetic field perpendicular to the static field and realize the similar type of magnetic field-induced spin resonance. But in this case, frequencies up to 100 megahertz have been observed, in this case from the group of Saigo Tarucha. What if you don't have if you don't want to use ferromagnets? For example, ferromagnets are not very compatible with CMOS technology. So another possibility is to use spin-orbit coupling. So if you have spin-orbit coupling in your system, then spin and orbital degree of freedom are not independent anymore. So shaking the orbital function will effectively result in a in a magnetic field on the spin. And this has been shown first in gallium arsenide quantum dots, where there is a little bit of spin orbit. And the effect it gets much stronger when you go to indium arsenide or indium antimonide material, where spin orbit is stronger. For example, with Rabi frequency, again, comparable to the one obtained with micromagnets. There is a third option, which is, again, related to spin orbit, but now via the anisotropy and the gate dependence of the G factor. So this mechanism was first studied in the group of David Ashalon and is known as the G-tensor magnetic resonance. So you have to think about the Hamiltonian for the Zeeman splitting of a two-level system. So it consists of this product of a tensor, the G-tensor, and the magnetic field. Now, in standard NMR, you would modulate the magnetic field, the perpendicular component, but you could equivalently modulate the G-tensor component. And so in this way, you may have a similar effect, provided that the G-tensor satisfies at least two important requirements. One is that it should be gate dependent, because you want to apply a modulating electric field and induce this way a variation in the G factors. And it should be anisotropic, and this I will explain you in a second. In practice, you can write down an expression for the expected Rabi frequency, and the Rabi frequency will have this term, which reflects the fact that, so for having a non-zero Rabi frequency, you need this term to be non-zero, and so you need the relative changes of the different components of the G factor have to be different. In a geometric analog, you can think the following. Imagine that you have, for instance, a cylindrical geometry with a parallel and a perpendicular component of the G factor. Suppose that for a certain gate voltage, the two components are this. If I now change the gate voltage and I obtain something like that, so I have an isotropic deformation of the G-tensor, in this case, I will have this term to be 0 and no G-tensor modulation effect. Instead, if the variation of the G-tensor is non-isotropic, like in this way, for example, then that term that I mentioned before would be non-zero, and then you would have a finite Rabi frequency. So now, if you want to see if this effect, if this approach is working, you need to study the G-tensor and its gate dependence and the directional dependence. So that's what we did. So we looked, first of all, let me say that for the case of electron, the G-tensor is pretty much isotropic. It's almost, G factor is almost equal to the bare G factor. So this effect will be negligible in the case of electrons. However, if we look at the holes, in the valence band, the G factor is no longer isotropic. This is known, and we knew it for example, for the case of germanium, where spin-orbit coupling is very strong. And then we looked, then we were tempted to look also in silicon, and so we performed the following experiment with a simple single-gate device, like the one I described before. Then we measure this at room temperature. This is a standard p-type transistor, but then when you cool it down, you see that the characteristic starts to develop some some sharp peaks. These are Coulomb blockade peaks that denote the addition of holes to the channel of the transistor. And this peak here, the first one here, is the addition of the first hole to the channel. For first hole, second hole, and third hole. So we looked at the stability diagram of this device, which is shown here. Again, you have these regions where this is differential conductance. The white regions correspond to Coulomb blockade. And so if you zoom, for example, around here, this is the domain where the channel is completely empty of charges. And the first diamond here, which is zoomed up here, is the domain where the transistor holds just a single hole. Okay, so what we are going to do now is to look at the G-factor properties of these holes, of this first hole. So this is second hole and so on. So let's look at the G-factor property, and this is a summary of the result we found. So if we look at the G-factor of the hole close to its ionization, so close to this charge degeneracy point, then the G-factor perpendicular to the plane of the device is around 1.8, but in the parallel plane is 2.5 along a certain direction. If we move to the opposite side, the perpendicular G-factor stays around the same, but the parallel one changes from 2.5 to 2.2. That's a significant change. In fact, this is a complete characterization that we did. So this is the anisotropic of the G-factor for, you see, moving, let's say, out of plane, between in plane and out of plane. So it goes from 1.6 to 2.5. And this is the anisotropy moving in plane at two different gate voltages, close to the ionization and to the addition of the second hole. So you see the anisotropy changes as I move from one side to the other. Now we can plug the numbers in our formula before and find out that the Rabi frequency, the expected Rabi frequency should be in the range of hundreds of megahertz. So a pretty fast modulation frequency. So now let's see, I will show you that in fact this mechanism is indeed effective. So for that, we need to be able to measure spin rotation, Rabi oscillations. And for that, we need to have a measurement scheme, and this measurement scheme relies on the spin blockade effect. So first of all, we use for this experiment a two-gate, double-gate devices. This time, this required the use of e-beam lithography, at least one e-beam lithography step, because the pitch between these two gates is pretty small. It's around 60, 65 nanometers. So that is at the moment not directly accessible without the use of e-beam lithography. So with this kind of device, we are going to operate it in such a way that we will form two quantum dots, one under each gate. So that's a diagram for electrons, but that's just to illustrate the principle. So we're going to bias these two gates, accumulate two quantum dots, use also the back gate as an additional tuning gate. And then what we're going to do, we're going to show that one of the two dots will act as a spin filter, in essence, and the other dot will act as our qubit. So the principle is shown here. For example, if you have the two spins on the two dots are aligned anti-parallel to each other, then it will be possible for this electron to go and occupy the same orbital state as this one, and then go out to the right. So this will result in a finite current through the device. However, if the spins are aligned parallel to each other, so they sit in a triplet state, then this process will be forbidden by Pauli exclusion principle. So in this case, we expect zero current through the device. So you see that this Pauli spin blockade effect provides you a way to know which spin orientation is on the left, provided the one on the right is always pointing the same way. So that will be our readout scheme. So what we are going to do in the experiment then is to apply an RF field on the first gate. If you believe what I told you before, through this G-tensor modulation effect, we should be able to rotate the spin and then probe its rotation by measuring current through the device. So here are some first experiments we did not long ago. So it shows you that, so you have in this plot here, you have a magnetic field and you have the frequency of the RF excitation. And you see that there is a straight line evolving linearly with magnetic field that indicates an additional current through the device. So you are in spin blockade. So as soon as, let's say, the left dot is occupied with this spin, then transport is blocked. But because we are exciting electron spin resonance on this spin, we are unlocking the blockade and then measure a finite current. So this peak that we measure here is a direct signature of electron spin resonance on the first spin, or all spin resonance in this case, sorry. So, and actually, it follows this linear relationship from which you can extract the value of the G factor that happens to be 1.63. Now, this is the dependence of the EDR signal as a function of the amplitude, so it scales linearly. That means that we are in the strong drive limit, and we can, by looking at the width of the EDSR resonance, we can extract a value of the Rabi frequency, which happens to be in the hundreds of megahertz. By looking at the lower side, we don't see any saturation. Saturation should give you an idea of what the coherence time of the spin is. We don't see saturation. This allows us to put a lower bound on the coherence time of the spin of 50 nanoseconds. But then we move a step forward. Now, what I show you is a continuous excitation of the spin on the left. We want to do now control rotation of the spin. For that, we need to excite the system in a regime where the electron cannot escape. And to do that, we need to combine the excitation, a burst of excitation, with a pulse on the gate that will put the device in a blockade stage. So you see the device is here, it gets blocked due to spin blockade. Then we pulse the gate, and we position the system in such a way that this electron will never escape. Even if I rotate it, it will not escape because I have Coulomb blockade. I'm in a Coulomb blockade regime here. And then I bring it back to the spin blockade, and then if I will see a current, it means that I have to rotate the spin. If I don't see current, the spin will be again in the blocked orientation. Okay, so these are the measurements. So I have now on this plot, and this color scale plot, the current through the device as a function of the length of the burst and the power of the RF line, RF signal. So you have cuts over here that correspond to Rabi oscillation of this spin. And you see that the Rabi frequency increases as I increase the power. You see here the different Rabi frequencies. And in fact, you can plot the Rabi frequency as a function of the voltage amplitude, the square root of the power, and it does follow a linear relationships. Now, the Rabi frequency can also be tuned if I detune my excitation compared to the resonance excitation, and this is what we observe here. That's the fast Fourier transform of the Rabi frequency that we observe. So this is the resonant condition around this value. So this measurement allows you to tune yourself very well in resonance with the system. And once you are in resonance, you can perform Rabi interference, Ramsey interference experiment. So Ramsey interference experiment consists in applying a pi over 2 pulse, so rotate into the plane, then let the system evolve in the free evolution in the static magnetic field, and then apply a second pi over 2 that will allow you to go either to the South Pole or back to the, no, actually, normally you would go back to the North Pole if you start from the North Pole. So in this way, by varying, let's say, this free evolution time, tau, you'll be able to measure the intrinsic decoherence time. And this happens to be in the range of 60 nanoseconds, free evolution decoherence time. So we also performed, so this is the same measurement where you have, let's say, the decay of the, as a function of the waiting time, the free evolution time. You see that the signal gradually lose coherence up to this point here. And these are two oscillations measured at this point, by varying the phase of this second pulse. So the phase can be varied with an IQ modulator. So in this way, you can perform a multi-axis rotation. So we have full two-axis control of the spin. And this is a measurement, echo-type measurement, also pretty standard for the study of qubits. So now we do a pi over 2. Then we do a pi pulse that should rewind, let's say, the dephasing, let's say, non-homogeneous dephasing, for example, due to the nuclear spins. And then we apply another pi over 2. So normally, if you use the same phase as here, then you expect this kind of decay, from which you can extract an echo time of around 250 nanoseconds. Whereas here, these are two oscillations obtained by varying this phase, one around here and one around here. OK, so to summarize, what I've shown you is that at the moment, starting from basically standard transistor technology, we have been able to control charge confinement in the system down to the few electron or few hole level with pretty sizable characteristic energy. We have observed spin blockade for both N-type and P-type devices. I didn't really show too much about that, but that's what we saw. And so we saw that in the case of P-type devices, we have this additional possibility to perform all electrical spin manipulation via the G-tensor modulation resonance mechanism. And then I've shown you some first measurements of Rabi oscillations in the case of P-type devices with Rabi frequencies that go up to around 100 megahertz. So it's pretty fast qubit. So compared to all other spin qubits, let's say this qubit, I would say, has a kind of average performance if I measure them in terms of number of pi pulses per coherence time. We are around 10. And spin qubits go between 1 and 100, sometimes 1,000 in the best cases. But well, the point I want to make here is that you should not take all these numbers as this definite number. This is a proof of concept experiment. Our goal was to implement a qubit in a CMOS technology. And now there's clearly a lot of work to do. We need to perform more experiments and then, let's say, extract more data concerning the characteristics timescales for spin coherence, and also look at the electron side as well. So there's a long list of things we need to do. So the first thing we need to do is to implement single-shot readout. What I've shown you so far is not single-shot. We are measuring just DC current. So to do that, we are going to follow this approach, which has been adopted by many other groups so far, which is based on gate reflectometry. You need to attach a tank LC circuit to every gate, and then measuring the reflected signal will tell you about charge displacement in your system. And then coupling this to the spin blockade effect will allow you to measure spins with a very large bandwidth. So on a very short time scale, which is what you need for doing single-shot experiments. So we have already done some first implementations. Here an example of reflectometry signal that you see here. So we have two gates, both connected to reflectometry tank circuit, to two circuits. So, so one of the gates is sensitive to charge on one dot. The other gate is sensitive to charges on the other dot, but they are both sensitive to transfer of charges between one dot and the other. And this is what you can see here in these lines. And here is a comparison between the reflectometry signal and the transport signal, which tells you that they both are able to access the same type of properties, at least in this regime. With a different reflectometry would allow you to operate also in the absence of transport. You don't need transport to measure measure charge displacements with reflectometry. So in particular, this data also give you an example of a spin blockade regime that was studied. So I need to speed up a little. I skip this. So here is an outlook. What we are heading for is this kind of geometry with while sticking to this nanowire transistor technology. So the idea is not to move very far from what can be done today in this platform. So we can envision to realize this type of devices. So it's a wire with a set of split gates. You see a basic example over here, with the idea that on one line we will have a line of qubit dots, and on this other line we'll have a line of readout dots, which will read out with the gate reflectometry. So in this way, we should be able to implement a linear chain of spin, which may not be the ideal geometry for large integration in the long term, but it is at least a good compromise nowadays to realize complex quantum circuits with the present technology. So and it is an example of a recent device that with this kind of split gate showing the operation and the confinement of these two tiny dots. You see, you have a completely empty channel here, and for this particular back gate voltage of -7, electrons are pulled toward the upper corner, and then you see here the addition of electrons to the two corner states. But if you apply a positive gate voltage, like here, now the electrons will be pulled more to the inner side, and then you will have, let's say, this kind of regime where they are both coupled capacitively to both gates. So, and these are let's say, the few electron occupation of these two dots. So this tells you that you have pretty much good control of where the dots are and where the dots sit, and that's very important for long-term prospects. So one last thing I want to say is about another interesting opportunity that comes with the use of CMOS, of a CMOS platform, is that this would naturally allow you to integrate qubits with peripheral electronics on the same chip. And peripheral electronics may imply, for example, low-temperature amplifiers, or multiplexers, or DACs or ADC converters. So we are working on that direction as well. And for instance, recently, I was not directly involved with this, but a paper was put out from our lab demonstrating a local oscillator at the gigahertz frequency operating at 1 Kelvin that was used to drive a single electron pump consisting of a device similar to the one that I've shown you with two gates. So you see you have a voltage control oscillator that produces 1 gigahertz signal, and then you have this signal is split in two, and one of the two sides is dephased by pi/2. And then these two signals are sent to this two-gate device to produce a current pump for current standards. And so here is a view of the device with the oscillator over here. This is a set of transistors that allows you to scale down the frequency to be able to measure it from outside. It's not very useful, but and then down here you have the two-gate double-gate device for implementing the pump. And this shows the clock frequency as a function of the applied potential, VCO, at different temperatures. So if you sit here, you see that your RF circuit oscillates also down to 4 Kelvin, and actually down to 1 as well. So I'm at the end, and of course, well, all I said would not be possible without the contribution of a bunch of people, starting from postdocs. Romain Morin is my postdoc who did all the recent experiments on the spin qubit. And then Dharan Patil, Andrea Korn, and Alessandro Kipp are postdoc and PhD student respectively, former PhD student, former postdoc, and then my colleagues, Marc Sanquer and Xavier Gel from our lab. We collaborate with Alexei Orlov from the University of Notre Dame here in US. And of course, we have close collaboration with people from the CMOS engineering department, the group of Maud Vinet. And also we have precious help from a bunch of theoreticians, in particular Jean-Michel Niquet, who provide us with very important input on the modeling of nanoscale transistors. So with this, I want to thank you for your attention. I was split off. Yeah,
because it should be spin 3/2, I guess.
No, this is, in fact, effectively, this one is a spin 1/2 system. All the degeneracy is lifted by confinement and strain. So you end up with a Kramer's doublet that you split in two. So we occasionally saw, but probably for a boron atom in a p-dope structure, 4-fold splitting.